Right. So the second problem we talked about is like the problem of frequency guarantees. And there are several subproblems. Actually, one subproblem I forgot to mention is the subproblem of non-realizability. So what is non-realizability? Non-realizability means that the real world is not described by any of the hypotheses in the product. People sometimes call it the grain of truth problem or the specified prior problem. Like in learning theory, it's usually called non-realizability. So what typically happens with Bayesian methods is that Bayesian methods have frequency guarantees in the realizable setting, but in the non-realizable setting, they in general don't. You can sometimes get frequency guarantees if you also make some ergodicity assumptions. And that's kind of, I'll try to maybe make it a little more tangible. Like, imagine that, So imagine that forgot which of those colors are good and which are not good. Oh, this is probably bad.
Yeah.
So this looks good?
Yeah.
Okay. So imagine that we want to describe an environment by like a Markov decision process, right? Or even just a Markov chain, right? It's just even if in the passive statement where we don't take actions, which is like forecast or something, that's already like an issue that you're trying to describe the world as having 5 states. And trying to learn like the transition probabilities between those states. But actually, what you think is a state is actually 3 different states. And this thing is actually 2 different states, and this thing is 4 different states. And this one is just a state, but this is also 3 different states. Okay. So the actual environment has like 6, 10, 13 states, right, instead of 5. In those states, they have some, transition probabilities between them. But now you're kind of trying to model this as something with less states. So what happens in this case is when the system reaches equilibrium, when this Markov chain kind of approaches equilibrium, you will be able to kind of describe it using this coarse-grained chain. Why? Because like in equilibrium, the distribution, so eventually the Markov chain approaches like an equilibrium distribution of the states. So inside this blue state, the distribution over those orange states will be something fixed. Right? Maybe like in equilibrium, this has a probability of like 1/2, and this has a probability of 1/3, and this has a probability of 1/6, for example. So now if I'm in this blue state, and I'm asking, okay, what are my probabilities to go to other blue states? Then they're kind of well-defined answer to this, which is just look at, where this state would go, where this state would go, where this state would go, and take like the convex combination of those three, coarse grain it to the blue ontology, and then like take the convex combination with those stationary probabilities. So there is some natural coarse grain Markov chain on the blue states corresponding to the Markov chain on the orange states. And you can actually show that a Bayesian learning algorithm would actually converge to learning this coarse grain region. So here things are kind of good. So in some sense, where is the problem? The problem is that there's like two big problems in this story. One problem is the ergodicity assumption is that this description is only good once you reach equilibrium on the orange states. Now, reaching equilibrium on the orange states is a really strong demand, if you think about it. Like, reaching equilibrium on the blue states is fine. The blue states are just some coarse grain description which you use to describe the universe. So maybe, yeah, okay, fine. This description eventually reaches equilibrium because that's what you need for it to be useful. But the orange states are kind of the real world, right? So the ultimate orange states are kind of the actual, like, microscopic full state of the universe. And that thing is not in equilibrium. Like, this thing will reach equilibrium when the universe reaches heat death. But that A will take a very long time, and B, by then, all of this won't matter anymore, right? So the universe is kind of on the microscopic levels, or on any level which is not like some very specific approximations, is very much not like an equilibrium state. And when you are not on this equilibrium state, then there's no like good frequencies guarantees that we know by Bayesian algorithms in the non-realizability. Yeah.
Can you describe a bit more detail about like what precisely you mean by like an equilibrium here?
So an equilibrium means that right. So an equilibrium means that every time you visit this blue state, you can half of the times you will end up in this microstate, 1/3 of the times you will end up in this microstate, 1/6 of the time you end up in it. So this kind of distribution of what the orange state is, conditional on what the blue state is, it kind of reached equilibrium, so it's approximately equal to a constant, and it doesn't like keep changing with some other underlying processes.
So part of this is also like how you encode the environment or something.
So it's part of what?
Like how you encode the environment. Like in theory, you could do this thing of like, if like it's like you could like one way you can encode this is like sort of just create two copies or something. When like maybe it's not in equilibrium, but like the first time you go to this copy and the second time you go to this copy or something. But then everything blows up, and that's kind of how you.
I mean, it kind of like depends on how you encode the environment in some sense, but it's kind of a big ask to have any encoding. But I mean, this orange encoding has to be like precise, right? The orange encoding needs to like capture the real like transition probabilities and not just be some coarse grain. So
right.
this, and the equilibrium problem is one problem, but it's not the only problem, because the second problem is that once you move from just Markov chains to thinking about MDPs, right? So now there's some particular actions that you take. So what happens is now the equilibrium distribution depends on your policy. So if you choose different policies, like your agent only sees the blue states. And it only takes actions that depend only on the blue states. But nevertheless, if it pursues, if you look like in two different, for example, different stationary policies on the blue MDP, then the stationary distribution over orange states, there's some underlying orange MDP, right? They will be different in those different policies. So there is not one correct answer in that case. Like in the Markov chain case, there was something which we could like in the ergodic limit, in the limit of in the stationary limit at least, there was some meaningful way to like say, okay, with like the real universe is not given by this coarse grain description, but there is some kind of a best approximation that we can make. But once we go to the active setting with MDPs, there is no such thing. There's no true blue MDP anymore. Like there's some kind of a weirder object which is like, for any policy, there's some different transition kernel, which is like not standard MDP at all. It's like my action on this blue state could affect the transition kernel in this blue state indirectly because it affects the probability distribution over the orange ones. So because of this, a Bayesian algorithm would not, it's just kind of, a Bayesian algorithm is prior just trying to describe the world terms of the blue MDP is not guaranteed to converge to anything good. And yeah, and kind of if you think about it, this kind of ergodicity thing is sort of related to out of distribution behavior for learning algorithms, right? Because like what does it mean to be like in distribution or out of distribution? So it means that like you can kind of model the world as being in some kind of an equilibrium distribution out of which you're sampling, and then like you kind of train yourself on this equilibrium distribution, you're in distribution. But like if you're not in the ergodic situation, then you don't have this. So in some sense, like being able to kind of deal with non-ergodicity gracefully, kind of this combination of non-realizability with non-ergodicity is pretty closely related to out-of-distribution learning. So this is like a problem. How do we solve this problem? Right? So in principle, in classical learning theory, the traditional approach to non-realizability is using what's called agnostic learning. So agnostic learning, the idea is instead of like converging to the true hypothesis, which we cannot do because the true hypothesis is not in the hypothesis class, we converge to the best approximation. We try to find out which converges to the best approximation of the true hypothesis. And this works pretty well in like classification, in regression learning, right? Because here it kind of makes a lot of sense. Like imagine if you're like doing, you're doing like polynomial regression or something, and you have some data points. So they're not described by the polynomial, but of degree 2 or whatever, but okay, you can like write some polynomial of degree 2, which is like the best approximation, and you can have some algorithm that converges to that. That kind of makes sense. But in the reinforcement learning world, it's kind of much more difficult to understand what does it mean to have the best approximation. So there is some work. There's not a lot of work on agnostic learning in reinforcement learning. There is some work in like the model-free setting where they're trying to say, okay, let's suppose there's some bound in the Bellman, like suppose that like the true environment can be like its state action value function can be approximated by something in our hypothesis class in the sense that the Bellman error is bounded by something, and then like we have a term corresponding to something in our data. So there's like some work there, but there's like still some limitations to this. But nevertheless, it's like one approach. So one approach is like agnostic. So we don't really have a very good theory of that, but there are some special cases where there are some results anyway. But yeah, this is like one approach. So this approach kind of requires to have some notion of like some kind of a metric or something metric-like, which says, how close is the hypothesis to a particular environment in some sense, and then like we can talk about like finding the best hypothesis, or like or like having some kind of regret that scales with the distance from how bad our approximation is. So this kind of agnostic approach is kind of motivated by thinking about approximate models in a very like classical sense, that you have a model that approximates something. But yeah, okay. So now there's a different approach, which is something that I'm advocating, but it also might be complementary, which we call Infra-Bayesianism. Okay, so what happens in Infra-Bayesianism? So in Infra-Bayesianism, this kind of draws on so-called imprecise probability theory, and the idea there is replacing probability distributions by some other object, for example, like Riddle sets. So yeah, I think we'll have a separate lecture on that. But like the basic idea is like instead of describing uncertainty using probability distributions, let's say the delta x is the space of probability distributions of x. Probability distributions of x. So we introduce some kind of box x, which is some more general thing. For example, box x could be like the set of all theta is a closed convex subset of delta. So instead of talking probability distributions, we talk about closed convex sets of probability distributions. For example, we just had x with just 2 points, and this would be the same as talking about probability intervals instead of exact probabilities. So what does it buy us? The thing it buys us is now the realizability assumption in the information sense is a much weaker assumption. Like maybe we cannot like describe the world as an MDP of just 5 states, but now we don't need to. Now we only need to describe it as an infra-MDP in 5 states. So what does it mean in infra-MDP? It means that now, like we have our 5 states, and now when you ask me, okay, in this state, if you take such and such action, what's going to happen? Instead of giving you an exact probability distribution, I'm giving you some set of probabilities, some set of probability distribution. I'm telling you, okay, you will go here with some probability that's between 0.2 to 0.8, and then you will either go, the rest of the probability distribution might be here, or it might be fully concentrated here, but it's definitely here, definitely not concentrated, like something like that. So it's kind of a little hard to diagrammatically explain what a set of district probability distributions in 4 states looks like, but it's something much less precise. And then this thing, it can capture what's happening here much better because, okay, now maybe there are like 3 orange states. So now maybe there are like those 3 orange states here. But that's okay, because this orange state has one probability distribution over the next blue state. This orange state has a different one, and this one has a different one. Now we can take just the convex hull of all three of those and say this is our kind of infra-probability distribution on what the next state is. So this gives us a manner to have those kind of coarse-grained descriptions of the world that doesn't, and now we don't depend on any like equilibrium assumption. So those methods are kind of conceptually different in the sense that this actually requires you to have a model which is a good approximation of reality for some kind of stringent sense that like whatever happens, it's always close to the model, according to some metric of closeness. Whereas here, you have like the freedom to be like completely agnostic about like entire parts of the world. You can be like, yeah, this part of the state space, I know exactly what's happening here. I have no idea. If you like hit this state, anything can happen, right? And like this is, so there's not like a constant approximation, constant degree of approximation. Like this thing is in some sense uniform, right? You need to kind of uniformly approximate the true world with your model. Whereas here, you can have like, you don't have such a requirement. You can have like some situations in which you have a very fine-grained description, other situations in which you have a very coarse-grained description. It's much more flexible. And this is something that is also like, an active research direction. So we haven't really understood the theory of Infra-Bayesian of red bounds very well. Like we only we understand some simple special cases, but there's it's much less developed than the classical theory of red bounds.